Yeah. So first speaker for today is Dieter Luz, and he's going to be telling us about the gravitino and the swampland. Dieter, I'll give you a heads up 20 minutes past your talk, so when there's 5 minutes left, and then another warning when you're out of time. And after 30 minutes, I will move the discussion to Slack, okay? Yeah, please go ahead.
Okay, thanks, Miguel. Perfect. Once again, thank you very much to all the organizers for inviting me for this conference. I feel honored to give this talk here at the beginning of the conference. And I will talk about the gravitino and the swampland, which is a joint work with Niccolo Scribiori and Marco Scalisi, and has appeared in April on the archive. So I think we know from recent experiments that apparently low energy supersymmetry is not really very much favored. And in fact, what we know is that the masses of all possible superpartners are at least in the TV region. So I show you a small plot about some charged superparticles, charginius, which are all not seen in experiments. So we have good exclusion bounds up to certain energies. So the question I like to ask, is there in fact a basic, a fundamental reason why we do not see supersymmetry? And actually, in the context of n=1 local supersymmetry, we all know very well that the spin 2 graviton has a superpartner, the spin 3½ gravitino. So the gravitino is also a very basic, a very fundamental particle, if you believe in supersymmetry. Moreover, the scale of SUSY breaking is set by the gravitino, and one can give a rough estimate, namely that the scale of the supersymmetry breaking is basically given by m3½ times the Planck mass. So I think quite model independently one can conclude that the gravitino mass must be at least above some certain millievolt. So I think this is a very strict bound, we know also from experiments. And therefore we can also rephrase the previous question and asking, is there any fundamental reason against the light gravitino? So that's basically the question I like to address in my talk. And what we want to do, we want to get information about the scale of supersymmetry breaking, namely about the mass of the gravitino by basic properties from quantum gravity. Actually, as you know, similar questions can be asked, for example, about the mass of the graviton itself or about higher spin particles. Very famously about the value of the cosmological constant. There is some nice work about how fermions are coupled to the swampland. So this is related to what I'm saying here. And even one can have some swampland arguments about the number of space-time dimensions. So let me very briefly review the idea of the swampland, and basically it is the question which infrared consistent quantum field theories cannot be embedded into a UV complete quantum gravity theory. For that, I like to show you this picture, I think, which is by now quite famous, thanks to Eran Palti. Here we start with the quantum gravity or string theory in the UV, and then going down to the infrared, say by compactification, a huge landscape of possible quantum field theories is opening up. But I think, as we also know today, there is also the swampland, which is surrounding the landscape. These are all seemingly consistent quantum field theories, like they are all satisfy a normally matching and all possible conditions you may think about in quantum field theory, but they cannot be completed into a UV complete quantum gravity theory. So I organize the talk in the following way. I will very briefly review some swampland conjectures. Then I will, as a precursor, discuss the so-called ADS distance conjecture. And this gives me a ground to switch over to the gravitino mass conjecture, the main part of my talk. And I will also discuss some of its phenomenological consequences. So let me start very briefly with the weak gravity conjecture, which I think is very well established and has very nice consequences and can also be very well tested in string theory. There is the electric version. So we are considering a U1 gauge field coupled to gravity given by this action. And there's the electric version, that is saying that there always exists a particle in the theory with mass m and charge q that satisfies this relation. So in Planck units, the mass must be always smaller than the product of the gauge coupling constant times the charge, or basically if you normalize the charge equal to 1, it says that the mass has to be smaller than the U1 gauge coupling constant. There's also the magnetic version, namely it's saying that the cutoff of the effective theory is bounded from above by the product of the U1 gauge coupling times the Planck mass. So again, in proper units, it says that the coupling is below the value of the U1 gauge coupling constant. So these are the two weak gravity conjectures, which are, I think, very well known by now. And in the context of the swampland, or in the context of the effective field theory, this cutoff is very often, it is energy dependent, and very often due to the appearance of so-called tower of states. And actually, if the swampland cutoff is lower than any characteristic scale of the effective field theory, then we would have to conclude that the entire EFT belongs to the swampland. So as I mentioned below, a kind of a generic picture is that there's an infinite tower of states with energies above the cutoff scale. So here we have the cutoff, here's the Planck mass, and in between there's this tower of states. And after having reached energies above the tower mass scale, at least we have to refine our theory to take into account also these additional states, which are also typically charged with respect to the gauge coupling. I think that Arnaud is raising his hand. So the chair, do you allow questions in between? I would do so.
Well, I mean, in principle, we're...
I'm happy to ask at the end. I didn't want to interrupt.
Okay, so then even better, then please ask at the end.
Yeah.
So this picture is also related to another swampland conjecture, the large distance conjecture. And it's saying that at large distances delta, in the parameter space, there must be an infinite tower of states, again associated to some mass scale. So this is the SDC. And put it into equation, it says that this mass scale is exponentially suppressed by the distance delta, which again means that the EFT breaks down at energies of the order of this tower mass scale. And as you can see from the simple relation, the swampland scale becomes very small, much smaller compared to the Planck mass when delta reaches very big values. In general, delta determines the so-called geodesic distance in the, say, scalar field phi parameter space of backgrounds in gravity. So delta is normally a field-dependent quantity. In case the associated scalar fields, here denoted by capital phi, have canonical kinetic energy, you may also want to add a potential. Then the distance is given basically by the field value of capital phi times some particular constant lambda. And if you have non-canonical scalar fields, non-canonical energies, you can do a field redefinition to reach also this form of the effective action. As it turns out, very often these tower states are due to the higher dimensional nature of the theory. So in other words, it is associated to the Kaluza-Klein mass scale, where a new dimension is opening up. And then this picture has the following form. The relevant mass scale is a Kaluza-Klein scale. Say if you compactify on a circle on a space with one volume R, then mkk is of the order of 1 over R. The corresponding distance is just given by the log of the R, and the relevant tower of states are nothing else than the kk particles with masses n over R. They are charged with respect to a U1 gauge group, and also the gauge couplings go like 1 over R. So you see that all kinds of conjectures are satisfied here: the large distance conjecture, the electric weak gravity conjecture, and also the magnetic weak gravity conjecture are all satisfied in this setting. Moreover, if we are considering other couplings in the theory, like masses or gauge couplings, they are all functions of the moduli scalar fields. And again, we like to know what is happening in certain limits in certain infinite distance limit, say if we send these couplings to 0, or if we send also some of the masses to 0. And in particular, we like to know if these limits are obstructed in quantum gravity in the sense that they are related to lowering the cutoff scale, the scale of the theory, and in the sense they are accompanied by a tower of states. And that is precisely, so this is basically the end of my short introduction. That is basically the question which we want to ask for, and the relevant mass scale m will be later on just the mass of the spin 3/2 gravitino. So, but before I like to come to the ADS distance conjecture, so which we considered together with Iram Palti and Kumon Wafa some 2 years ago. And for that, we like to consider ADS vacua of some certain dimension little d in quantum gravity, and they lead typically to a negative cosmological constant. And here the claim is that there exists an infinite tower of states with a mass scale m, with a tower mass scale m, which is proportional to a certain power alpha of the cosmological constant. And the conjecture is also saying that alpha must be positive and should be also bigger than 1/2. It means also, as a side remark, that ADS-D basically cannot exist alone as a consistent background if you make lambda smaller and smaller. So if you decompactify the ADS radius, a certain tower of states should pop up. And for example, in terms of an extra compact space, and I think this has also interesting implications for the dual CFT description, which was considered in several papers. Let me also mention that the bound alpha equal to 1/2 is saturated or should be saturated for supersymmetric ADS vacua. And this problem is also related to the so-called scale separation problem, which was also investigated by several authors. There is still some debate in how far it is satisfied or not, but for many known backgrounds in string theory and M theory, it is indeed satisfied by the tower of KK modes. Okay, this is the so-called anti-de Sitter distance conjecture, but we could be a little bit more courageous and try to also apply it to de Sitter or metastable de Sitter vacua if they exist. But we could try to apply this conjecture also to backgrounds with a positive cosmological constant. And in this case, if it would be really true, the ADC would lead to a very very spectacular prediction, namely there should be a tower of masses as light as 10 to minus 120 times the Planck mass, because we know that the observed cosmological constant is as small. And in this case, one would have to ask, what is the tower of states? And if it exists, why it escapes observations. So this would be a very, I think, strong prediction. I think it is not excluded completely by experiment, but one could raise some doubts if this prediction is really true. And therefore, perhaps we like to refine the ADC in case of broken supersymmetry, and then also apply a similar conjecture also for backgrounds for vacua, which have possibly a positive cosmological constant. So this is the plan, what I will now discuss in the following. And this brings me, in fact, to the gravitino mass conjecture. That is a paper we wrote together with Nicolo and Marco. And I should also say that basically at the same time, next day, there appeared also a paper by the Madrid group, by Castellano, Font, Herald, and Ibanez. The content of the paper is very much related to ours. They call it the gravitino distance conjecture, but if you read carefully our paper at some page, we also call it the gravitino distance conjecture. Also, our title is the gravitino mass conjecture, but this doesn't make a very big difference. And the conjecture is very much in the spirit of the conjectures or the statements which I have discussed before. Namely, it says that in the limit of small gravitino mass, there exists an infinite tower of states with some tower mass scale n, which behaves in terms of the gravitino mass in the following way. it behaves as m3½ with some power n. And this n is, so to say, the relevant parameter of this conjecture, which I try to compute also in some of the microscopic string theory examples later on. And again, in order for the conjecture to make some sense, n should be a positive number. Let me first go quickly back to supersymmetric ADS spaces. And there we know that m3½ square is just proportional to the minus of the cosmological constant divided by 3. So in this case, for supersymmetric ADS spaces, we see that the ADC and the GMC, the gravitino mass conjecture, are completely equivalent to each other. And I think this is nice because for supersymmetric ADS spaces, the anti-de Sitter conjecture turned out to be kind of successful. And I think then it's also good that these conjectures should be equivalent to each other. By the way, m3½ is the mass parameter of the gravitino in the Lagrangian, so one should not be too much confused about the fact that the gravitino mass is non-zero in supersymmetric ADS vacua. This is not a breakdown of supersymmetry, it's just as the gravitino mass behaves for supersymmetric ADS spaces. I also want to mention that the case m3½ is 0 is special and is not really continuously related to finite m3½. So basically, I always talk about instances where m3½ is non-zero, maybe tiny, but not completely 0. Okay, but however, in case of broken supersymmetry, the situation is different, and there, as a general relation, one has that m3½ square is always bigger than minus lambda cc over 3. And in this case, the ADC and the GMC indeed lead to different conclusions. In particular, now we can also allow for situations, or the GMC allows for situations where we can send the cosmological constant to 0, but still keeping m3½ finite and having no tower of light states. And that was just the situation which I mentioned before, where we have a small cosmological constant and would have a light tower of states. The GMC somehow would bypass precisely this problem. Okay. Let me give you two arguments or two general scenarios why the gravitino mass conjecture has a chance to be true. The first one is basically compactification, and then the gravitino mass is related to extra dimensions, and it then follows from the standard distance conjecture. But there's also another interesting case where indeed the gravitino is also charged with respect to some U1 gauge group. So there's a U1 gauge coupling, and in this case, the gravitino mass is related to the value of this U1 gauge coupling. In this case, the gravitino mass conjecture follows from the magnetic weak gravity conjecture. So I briefly discuss these two cases. First, the case of compactification. Here we like to study as effective field theory, the NP1 effective action, which contains, besides the gravitino, also a certain number of scalars phi. They are the moduli of the compact space typically, and of course they have also some fermionic superpartners. Then, as we know very well, this effective field theory is characterized by a scalar potential K and a superpotential W. There could be there are also gauge kinetic functions and maybe some other ingredients which are not relevant for me at the moment. And the kinetic terms for the scalars is given by the second derivative of the scalar potential as written down here. Furthermore, we know that supersymmetry is spontaneously broken in case the so-called F terms take non-zero values. The S terms are written here. They are given by the derivative of the superpotential plus the derivative of the scalar potential times e to the k half times W. And this can be also written in short by this expression where the G function is just the scalar potential, the sum of the scalar potential plus the logarithm of the superpotential square. So these are the F terms. Moreover, the gravitino mass square is also given by K and W in a very simple form. It is e to the K times W square. And finally, as you know, we can also compute the scalar potential, which means the cosmological constant as being the sum of two terms. The first term I call the gravitational potential, which is -3 times e to the G. And the other term is related to the F terms, it's related to supersymmetry breaking. And therefore, the gravitational part of the potential is always negative. It's -3 times m3 square. And from that, we indeed now see that the relation m3 square must be bigger than minus. I think the minus is missing here. Sorry for that, -3 times lambda over 3 in case of VF non-zero.
Dieter,
okay.
This is your 5-minute warning.
Okay, thank you very much. So very briefly, we can consider, for example, Calabi-Yau compactification, then the KK mass scale to 4 dimensions, then the KK mass scale is 1 over the volume over 2/3. The Kähler potential is proportional to some parameter alpha times the log of the volume, perhaps plus some extra piece. In the minimum, in many cases, also the superpotential is proportional to the power, is proportional to the volume of some power, beta over 2. In this case, we can compute the parameter n, which appears in the gravitino mass conjecture. It is 4 over 3 times alpha minus beta. And now, depending which kind of compactification you are looking at, you can compute this parameter n. So I give you very briefly, because time is becoming a little bit short, a few examples. For example, for KKLT-like compactifications, n is 3, but there are also log corrections because of the effective field theory on the warped throat. For non-supersymmetric Minkowski vacua, which are very interesting, so-called Schwarz vacua, the superpotential is constant, and then we get n is 4 or 3. And you can also consider, if it exists, the non-supersymmetric de Sitter uplift, and then also n turns out to be 1 over 3. Okay, so that is really the, more model dependent what the value of n is, but you can compute it for a large class of compactifications. And I think also the paper of the Madrid group, which I have mentioned before, does this for many instances. I also want to mention very briefly the second reason why the gravitino mass conjecture is true, namely when the gravitino mass is related to your U1 gauge coupling. This is precisely the case if there is an underlying n equals 2 supersymmetry. Then the graviton, the gravitino, the two gravitino appear together with a U1 gauge particle, or spin 1 particle in a common multiplet, that is a graviphoton. And now, going through some formalism, here the discussion would be a little bit more technical. Using the n equal 2 prepotential, one can indeed show that m3 is proportional to g3, which is a gauge coupling of the gravitino. And therefore, you see, sending this gauge coupling to 0, the gravitino mass would be also small. And this would be against the weak gravity conjecture. And in fact, a global symmetry with respect to the graviphoton U1 would open up. And therefore, a small gravitino mass is also vetoed by this argument. Okay, I think I have 3-4 minutes left over. And these I want to use quickly to use some phenomenological applications. Actually, first, I want to remind you about what is the quantum gravity cutoff, namely the scale where gravity becomes strong in a effective field theory, which is coupled to certain species, like the Kaluza-Klein tower or the other towers. Namely, in 4 dimensions, the cutoff scale is m Planck divided by square root of n. In other dimensions, we would get simply different powers for n. And in case the species are built by the tower of states, like for the gravitino conjecture, we get the following estimate that the quantum gravity cutoff is given by the Planck mass times m3 over m Planck to the power of n over 3. So this n is precisely the n which appears in the gravitino mass conjecture. And again, for several models, you can use your favorite value for n to see how the quantum gravity cutoff depends on the gravitino mass scale. Actually, using this relation, it's easy to see that M3 half is smaller than the quantum gravity cutoff only for n equals for n smaller than 3. So this gives you basically a restriction on the values of n, at least if you want to describe supersymmetry breaking, the effective field theory, because otherwise the scale of supersymmetry breaking would be above the cutoff, and then we would not even talk anymore about an effective field theory for supersymmetry breaking. All right, so we can apply this now for
Peter, just to let you know, you've run out of time. You're entering the question time, and I remind you that after 5 minutes, I will cut the discussion and move it to slide.
Okay, so I will be brief. So for cosmic inflation, we know that the inflaton, the inflation scale, also has to be smaller than the quantum gravity cutoff. And this will then, if you put things together, give you another interesting bound, namely that M3 half must be bigger than some power of h, namely h over 3 over n. And you can apply this, and typically you get that the SUSY breaking scale must be higher than the scale of inflation. Using also the input from the cosmic microwave background, namely from the tensor to scalar modes, which puts h in which you can h expressed by the parameter r in this way. We also get another relation, and that M3 half must be bigger than a certain power of r, and with r smaller than 0.6. You know that M3 half must be bigger than something like 10 to 2 GeV, at least reaching the sensitivity of next experiments. This can be also put into a nice plot, which I think you can see in the paper. And with that, I basically like to finish my talk. We have seen that there are various swampland conjectures. Many of them are related. I think hint at some deeper origin. Here we have discussed specifically the ADC, the conjecture which deals with the cosmological constant, and the GMZ, the swampland conjecture which deals with the gravitino mass. I think it would be nice to see if there's a parametric link between these two quantities of the following form with some additional parameter P. They are strong in constraints from inflation on M3 half, namely that the SUSY breaking scale must be order or higher than the scale of inflation, just based on these general arguments. You can plot the relevant scales on this diagram. And finally, let me perhaps conclude with this hopefully not too discouraging remark. So if you see here the picture of the swampland, I would conclude that indeed low energy supersymmetry apparently belongs to the swampland. And with that, I'd like to thank you.
Okay, thanks a lot, Dieter. We have time for, I think, just one question from Alan. And I remind everyone that you can that we can keep discussing about this on Slack later on. So you join the Slack channel and ask your questions there.
Okay, thank you very much, Dieter, for the interesting talk. You started, I think, also ended the talk by sort of asking about the prospect of supersymmetry, or saying that supersymmetry is disfavored as a low energy symmetry. So, I mean, to me, there's a more basic question, which is whether the Higgs is fundamental or composite. And do you know any string models or setups where of composite Higgs?
Yeah, actually not quite. I mean, we all know the reason why the motivation for low energy supersymmetry, that is a hierarchy problem. And if low energy supersymmetry is not there, we have to think about different reasons why the Higgs is small. One reason could be compositeness of the Higgs. In this case, supersymmetry would be broken at the string scale. And I know that many of you, I think also Ellen, are looking at these kind of models. And I think they would be favored by these kind of arguments. However, I'm not really aware of any good working model like Technicolor or something like this, where the Higgs is composite in string theory. Most of the model builders, I think, assume that the Higgs is an elementary particle.
Right. So what do you think about the prospect of experimental prospects of deciding whether it is composite or fundamental?
I mean, there are good experiments who can decide this. Technicolor, one can push up this Technicolor scale up to some value. So far, there's also no sign for composite Higgs, but I think this is a experimental question. You know that compositeness is also related to conformal field theory and to holography in some particular way. It's not excluded, but I think also composite Higgs is not really favored so far by experiment. It's also under tension.
Thank you.
Okay, thanks a